Yes.
Yeah, well.
I now live with my parents and 2 cats. That's how
Right.
far I've come.
And I always have the chance that a 5-year-old crawls
Yes.
across my screen. So there
We're looking for it.
Exactly. That's today's Easter egg.
Yeah.
All right. So yeah, we're in Switzerland and Berlin, so we'll start on time. So welcome everyone. Thanks for joining us for the second session of our virtual digital economy seminar. We have a fantastic speaker again with Avi Goldfarb. And so very briefly, the formalities for today. The moderator will be Imke Aimes at the Northeastern University. And if you have any clarification questions during the talk, send these to Imke in the chat window. She will either ask the question to the speaker directly or unmute you to ask the question yourself. For the Q&A after the talk, we'll collect questions in the same way. One final announcement, the seminar will be recorded. So if you do ask a question yourself, you will be on the recording. So Imke?
Yeah, thanks, Hannes. And yeah, thank you all for coming here. I'm excited to introduce Avi Goldfarb, one of the many people who don't need an introduction here. But thank you, Avi, for coming here or giving a talk here. We'll listen to him today talking about machine learning as a general purpose technology, which is broadly co-authored with Bledi Tasca and Florenta Teodoridis. So Avi, the floor is yours. Thank you.
Okay, thanks everybody. Thanks for coming, and thank you guys for organizing this. I think this is a great service to the community. And then just scrolling through names, it's nice to see lots of familiar faces and lots of people I know. So so thanks for tuning in, and for those of you who I haven't met before, hopefully someday that will be we'll get to meet non-virtually, like genuinely in person. So this project is an ongoing project with Florenta Teodoridis, who's a professor at USC, and Bledi Tasca, who's at Burning Glass Technologies, and you'll see why Burning Glass is a key part of this, because we're using their data. And so the big question that we're aiming at in this paper is, should we think about machine learning as a general purpose technology? So for those of you who don't know, about 3 years ago, we hosted a conference in Toronto on the economics of AI, and that turned into this conference volume. And in that conference volume, and at that conference, theme number 1 was that artificial intelligence, the recent advances in artificial intelligence, could be seen as a general purpose technology. At least that was the hypothesis. And so why does that matter? Well, if AI is a GPT, that means slow growth today and fast growth tomorrow. So Brynjolfsson, Rock, and Syverson have this paper on AI and the modern productivity paradox, where one of the highlights of that paper is comparing computing with electricity and saying it took a good 50 years after the first commercialization of electricity till we saw a productivity boom in electricity. And they argue that we're about 50 years after the first generation of IT, commercialization of IT, and AI they hypothesize, could be the technology that leads to a sharp increase in productivity. But general purpose technologies mean slow growth today, fast growth tomorrow. Coburn, Henderson, Stern's chapter emphasizes that AI, machine learning in particular, is an unusual kind of general purpose technology. And what they mean by that is it's not just a technology that can be widely used and involves cutting edge science across, and is useful across a wide variety of industries, but it is an input into the innovation process. So they argue that it's both the invention of a method of invention and a general purpose technology, which again should accelerate growth once people figure out how to use it efficiently. Manuel Trachtenberg, who's one of the people who, one of the co-authors in the original GPT paper, said if AI is a GPT, then that means we have to transform the way the education system works. in order to take advantage of in order to make sure the workforce has the skills required in order to use a GPT. Now, so the conference volume, if AI is a GPT, there's all sorts of consequences that we should expect, but we actually don't have an answer of whether AI is a GPT. And so what we sought out to do in this paper is to answer the basic question. So, is artificial intelligence GPT? And in doing that, we went back to the literature that tried to identify other GPTs. And what we found is there's a lot of ambiguity in thinking through what a GPT really might be. And all of the literature that says this is a GPT has the benefit of something like 50 years of hindsight. And so what we're trying to do in this paper is to get a leading indicator of whether something is more or less likely than other technologies that exist today to be a GPT. In some sense, you can't really define it without decades of hindsight, because then you know what the productivity consequences were. But when we're in the moment of the technology diffusing, that's not very useful. And so what we're trying to do in this paper is build on others who've looked at, who've identified GPTs based on, at least 50 years of hindsight. Like in Lipsy, they go to tens of thousands of years of hindsight to really try to say, what does it mean for something to be a GPT, and can we identify that in data? So what we do is we take data on millions of US job postings, and we're going to examine which organizations and locations post AI job vacancies. So in particular, we're going to look at the kinds of organizations and the diffusion, essentially by industry, that post jobs. I say AI, but really it's posting machine learning job vacancies. And we're going to argue that adoption of AI measured by hiring shares many features of what Bresnahan and Trachtenberg label as the characteristics of a GPT. Other recent technologies actually do not share these features for the most part, although you'll see that the thing we're calling machine learning, we have some new sort of hot off the press results that weren't in the paper distributed that suggest that data science in particular is another name for machine learning. And so those technologies seem to go together. The broad agenda of this paper is it possible to identify a GPT early on, or do we have to wait for the consequences to play out? And we're going to obviously argue that we have some suggestive evidence to suggest that, suggestive evidence that machine learning is really a GPT. Okay, is likely to be a GPT. So before I describe what we do in the paper, there's two things that we need to unpack. The first is, what are we talking about when we're talking about AI? And the second is, what are the characteristics of a general purpose technology? And so when we think about AI in the popular press, we have this this idea of robots that can do just about everything humans can do. So the optimistic scenario that we see in science fiction and the press is something like C-3PO. What is C-3PO? C-3PO is a robot that can do just about everything humans do. C-3PO does at least two things better than human. The first one is sort of a key part of the movie, which is that C-3PO can translate and calculate probability, stuff like that. The second one is less obvious, but it's what makes C-3PO optimistic, which is that C-3PO listens to humans. So C-3PO is better than human, even though Star Wars is not, as far from utopian. On the robot side, it's pretty positive in the sense that the robots tend to listen to the humans. The rest of science fiction is filled with robots that don't listen to humans, but can also do just about everything humans could do, and maybe more. And that's where we get, Skynet from the Terminator, or the robots from the Matrix, etc. Now, this idea of true artificial general intelligence, I used to think it was crazy. And then at our first AI conference, there was an argument or discussion, let's call it, between Daniel Kahneman and Jan LeCun. And that conversation convinced me, at least, that this is possible. Many of you may have thought it was possible already, many not. And Kahneman concluded with this story where he said, a novelist wrote some time ago that he's going to write a novel, and the novel would be a love triangle between two humans and a robot. And he wanted to know how the robot would be different from people. And Kahneman proposed three main differences. First, the robot is better at statistics. and doesn't need a story. So if he was telling this to a robot, he wouldn't have needed that first paragraph. Second, the robot would have higher emotional intelligence because the robot wouldn't get angry or frustrated or anything like that and would be able to respond and predict human reactions. And third, the robot would be wiser because it would have a broader set of experiences because it could take from lots and lots of other robots. But his core conclusion was he didn't think that there's very much that computers could do that that humans could do that computers wouldn't eventually learn to do. And that was also consistent with Jan LeCun's point of view. And so it started with the disagreement, and it ended up being they both agreed that someday the robots will do everything we can do. That said, if you ask them when, it's very clear this has very little to do with today's excitement around AI. The reason we're talking about AI today, and we weren't really talking about it 15 years ago, has nothing to do with this idea of artificial general intelligence. It's a very particular technology called machine learning that's gotten much, much better. And if we think about what machine learning is, this is prediction technology. So the field of machine learning that really has driven the most excitement around, in the press and around commercial applications is a field called deep learning. And the sort of maybe the inventor or discoverer, he calls himself a discoverer of deep learning, framed it like this: take any old problem where you have to predict something and you have a lot of data, and deep learning is probably going to make it work better than the existing techniques. That sounds a lot more modest than artificial general intelligence, okay? But it's still a big deal. And in particular, if we think about these, so this is, I'm going to plug my book a little bit. If we think about prediction as using information you have to generate information you don't have, what's changed in the last few years is this drop in the cost of prediction. And so prediction technology is a big deal because it helps us make better decisions. So it's not, we're far, far away from an AGI. We are not near artificial intelligence. It has been 20 to 50 years away since the very first AI conference at Dartmouth College in 1956. And it continues to be 20 to 50 years away. 20 to 50 years away is not never, but it's not what we're talking about today. What we're talking about today is machine learning. So we need, I'm gonna, for the rest of this talk, use AI and machine learning as direct substitutes for each other. So, as Jay Joshua and I have argued in a number of books, if we want to understand the consequences of AI, we have to think about it, how it's going to impact decision-making. And the fact that decision-making is a big deal suggests that AI might be a general purpose technology. So the other piece, in order for for you guys to essentially care about what we're doing in this paper, is to unpack what a general purpose technology is. And so general purpose technologies were introduced in this paper by Bresnan and Trachtenberg in the 90s. And the essence of a general purpose technology is that it sits at the intersection of micro and macro. So it's where the economics of innovation meet the economics of growth. And so the examples they use are the steam engine, electrification, computers. So point number one is when we think about general purpose technologies, they're rare. So the microwave oven was a very transformative technology in lots of ways, but it wasn't a general purpose technology. It didn't have a long run impact on productivity and society at large. But the thing to recognize is for general purpose technology to matter, the productivity impact takes some time. And so what has to happen for a general purpose technology to take hold and even be a general purpose technology is that something is invented in a producing industry, okay? Whether it's a new use for a steam engine, a new steam engine, direct current or alternating current for that matter, computers, and then that's pushed to a using industry. So someone actually uses the technology. What makes it a general purpose technology is that the using industry then invents on top of that technology. So the using industry innovates, and then that innovation in the using industry feeds back into the producing industry. And so we end up having a positive feedback loop between using and producing industries, which then pushes against the standard growth model, decreasing returns to innovation. So we have this feedback, producing industry innovates. Oh, here's deep learning. using industry innovates, oh, deep learning is going to be useful for this particular application, building a chatbot. Then producing industry innovates again. Oh, if we're going to do something like that, we need to innovate on the language side of things, the basic tech. Then the using industry innovates back, and we get a back and forth. So Bresnan and Trachtenberg highlight there's a handful of these general purpose technologies, and pervasive use in a wide range of sectors and technological dynamism. Technological dynamism is just sort of at least by my reading, it's a way for them to not include the hammer and nail as a general purpose technology, but it's a way to make sure that it's science-based in some way. So most general purpose technologies play the role of enabling technologies, opening up new opportunities. So it's not, electricity was more than just a reduction in energy costs. It allowed people to change the way factories were run and organized, for example. And so they call this idea innovational complementarities. Later work in the IS literature, Lin Wu and Eric Brynjolfsson and others have highlighted this as have highlighted the complementarity aspect to it. And on the organizational complementarities is what they often call it. And then on the invention side, so Shane Greenstein and Tim Bresnahan have called this co-invention. These are all the same thing: innovational complementarities, organizational complementarities. Co-invention is just ways that downstream industries, the using industries, innovate on top of the producing industries. And so Bresnahan, in a later handbook chapter, highlighted the ways we could identify a general purpose technology explicitly. Oh, this one is and this one isn't. Okay. And so the first thing he highlighted is that they're widely used. They're adopted across many industry sectors. Second, that they're capable of technical improvement. So we have evidence of cutting edge innovation. Third, that there's innovation in application sectors. So this is going to be something that we're going to lean on in this paper relatively hard. So it's not just that there's innovation and it's widely used, but the innovation is on the research side of things rather than on the rather than not just on the using side of things. So the using industries are innovating, and so the last piece is co-invention. It's going to be a little bit harder to nail down in data, but a GPT, it's not just that there's going to be technology focused research. There's also going to be co-invention or organizational complementarity. So we should expect the way organizations are run that use this technology to change. Now, how are we going to define that? We're going to leverage some work that Shane Greenstein, Chris Foreman, and I did a few years ago, and to identify co-invention in the internet context and look at places where it's likely to be relatively easy to invent. So if AI is a general purpose technology, we expect it to be widely used, capable of ongoing technical improvement, enabling innovation in application sectors, and to occur in places that have relatively low co-invention costs. Okay. The core thing I'm going to present over the next 25 minutes or so is going to be leading to something that looks like this scorecard. So this is going to be the data that we showed in the paper that was distributed, where we're going to look at 9 different technologies and assess under these, under Bresnahan's widely used, capable of ongoing technical improvement, innovation application sectors, co-invention costs, seems to be consistent with machine learning being general purpose technology. Interestingly, in this data, there's a sense that cloud computing might also be. Now, over the last couple of months, and really hot off the press in terms of the last couple of days, we've looked at an alternative and wider set of technologies from the Gartner Hype Cycle. So rather than just these 9, we've added a whole bunch more. And this has led to a couple of new insights, which we'll unpack as we go on. But insight number one is that machine learning and data science really move together, and it's hard to think about one as separate from the other. And insight number two is that increasingly over time, research jobs in particular that ask for any of these skills also ask for machine learning. So if you're doing research across a wide range of technologies, you're also being asked if you have machine learning skills. Okay. There's two open questions that many of you might already be asking and thinking about. The first one is, why does it matter if AI is a GPT? There's an sort of a core economics concept on how to think about this in terms of economic growth. And then there's a more managerial focused concept on how do we, if we are thinking about investment strategy, not at the policy level, but at the firm strategy level, we should recognize the need for co-invention and reorganization if this really is a GPT, so that, in order to use it and benefit from it, we also have to be inventing. The second question is, don't we know this already? I would look, this is a little strange coming from me because we published that book 3 years ago or 2 years ago saying if AI is a GPT, it's a big deal. And the only reason we published that book is because AI could be a GPT. At the same time, I've always felt a little bit uncomfortable. And if you look at the language we use in that book and elsewhere, it's if AI turns out to be a GPT, if AI, there's a lot of if. And so what we're trying to do in this paper is unpack that if. So don't we know this already? One version of this is if you look in the empirical literature, the literature on GPTs, for example, in IS, information systems, yeah, they assert that we already know that machine learning is a GPT and AI is a GPT, but they also say cloud is a GPT and blockchain is a GPT and distributed computing is a GPT and VR is a GPT. And our purpose here is to separate which of those kinds of technologies are more and less likely to really be transformative in the sense of leading to this positive feedback loop between producing and using industries. So that's the setup. Maybe now's a good time to pause for questions. If we have any. Nope. Okay.
Nope. All good so far.
All good so far, or everybody's just got a repeat video of them just going like this.
Actually,
okay.
Just got a question from Hong.
Okay.
So, Hong, you're unmuted.
Oh, okay. I thought you would just relay the question. So, hi, Barbie. Let's see.
Hi.
So is the feedback loop necessary?
So
I think it's helpful, but is it necessary?
So for something to be a GPT, yes, the feedback loop is necessary, in the sense that without the feedback loop, you get diminishing returns to the innovation kicking in quite quickly. It's the feedback loop that enables the sustained productivity advantage. I should add the caveat that empirically, we're not going to be able to identify the feedback loop. Empirically, we're going to be able to identify whether using industries are innovating, or at least are hiring innovators, which is a long way from the feedback loop. But the model explicitly requires that feedback loop, or else you get to your standard growth model of diminishing returns to any innovation.
All right, that's
okay.
all we got so far.
That's all we got so far. Okay, thanks, Tom. It's good to see you. Okay, or at least you didn't even have your camera up, so connect with you. Let's call it that. Okay. So what do we actually do in this particular paper? What we're leveraging is Sunny Tamby's insights, along with Lauren Hitt, that hiring decisions can help us understand technology adoption and diffusion. So across a wide range of industries, we're going to look at hiring, both in terms of, hey, did this industry hire? And second, did this industry hire in a research-oriented job? This is all going to be descriptive stats, just to, for those of you who were getting ready to debate instruments and causal inference. don't worry. There's none of that here. This is, we got descriptive stats and assessing whether those descriptive stats are consistent with the demands of a mod, of the GPT model. Are they consistent with, are those underlying correlations and even like means and averages and Gini coefficients consistent with what we'd expect if machine learning is a GPT? Okay. That's the main results. We're also gonna, I'll detail this later, but we're gonna rerun what Shing Greenstein, Chris Foreman, and I did way back in 2005 and 2008 in the work that when Chris and I were Shane's RAs that came out of that a long time ago. We're going to replicate that where we did it for internet. We're going to replicate it for machine learning and in other technologies.
Sorry, Avi.
Yeah.
Seems we have one more question from
Right.
Brian Wang. I'll just unmute him as well.
Okay. Hi, Brian.
Yeah.
Hi, can you hear me? Hi, can you hear me?
Yes.
Sorry for that. Just wondering on the definition of is it called general purpose technology, right? GPD. If in the case is if I have machine learning, for example, it generates another technology later, which is kind of more like a GPT. Like if I have a kind of a parent technology which generates another GPT, should I define the parent technology as a GPT as well?
So this is almost deliberately ambiguous. So
yeah, kind of
the sharp line between
that,
look,
yeah.
we have the insight, maybe going back to like Ada Lovelace and Babbage, that we can do a lot with digits. Is that the GPT, or is the GPT the actual Turing machine, or is it the semiconductor, the ability to convert semiconductors, or is it the personal computer, or is it distributed computing, or is it statistics, or is it machine learning? There's ambiguity there.
Yeah,
and there's no sharp answer on where the line from one technology ends and the other one begins. Nevertheless, it's useful to think about categories. And so in some sense, every technology, it's hard to really say, oh, all of these technologies rely on farming because otherwise we wouldn't be able to eat, right? That's and have enough resources to invest in science. So you got to draw the line somewhere. Nope, that was so.
And actually, sorry if you don't mind, there's one more clarifying question from Dimitris Mavridis.
Okay,
yeah,
great.
I'll let you go.
Let me just finish that one, and then Dimitris.
Sorry.
So, so my sense is there's enough differences in how people describe machine learning from internet, from hardware, like from semiconductors, that we could think of these as three different technologies. And one of the things we're going through in our current exercise is to try to see which skills tend to be required in the same job as a measure for how distinct these pieces are. And what we're going to find is, as I hinted, that like machine learning and data science are really in many ways the same thing, but the other technologies are different, but increasingly machine learning is an input into the other technologies, but not vice versa. And that is how we're going to think about unpacking these things. Next question.
Okay, sorry, I got one more from Dimitris Mavridis. So.
Hey,
hi.
I don't know whether I'm being heard.
Yes, you are.
Yes.
Okay, hi. So thanks for taking the question. So I'm looking at the keyword strategy that you actually presented just a slide ago, slide before, and I'm looking only at white collar, high skill jobs. Is blue collar, sorry?
Oh, I don't remember talking about that yet. Okay.
Oh, okay.
But so hold that thought, because I accidentally hit the forward key, and I thought it was it was less than half a second, so I'm impressed that you absorbed it. But let's get there and then get to that question, because it's
thank you.
And I'll try and anticipate what I think you're going to say when I get there. Okay, so here's the data. The data is from Burning Glass. It's over 40,000 online job boards and company websites to aggregate job postings and create these. That's what they do. They're a company that's a HR analytics company based on vacancy data. Okay. They believe they have the near universe of jobs that were posted online in 2007 and from 2010 through actually now 2019. We're going to focus on 93,000 job postings in the US for the main results through 2018. And then for the newer stuff, we actually have through October 31st, 2019. There's weaknesses in this data. It's vacancy data. It is not, does this company use this technology in some deep way? And it's not totally representative of jobs. And so there's a paper in the AER that uses this data that spends a fair bit of time looking at biases in the data. And there are several, but we don't have a ground truth. So it's hard to really think about what these biases mean. But compared to the other occupational databases we see, Burning Glass is overrepresented in computers and math. It's overrepresented in other white collar jobs, and it's underrepresented in in transportation, food preparation, etc. That might be an issue if we're thinking about the overall prevalence in the economy of any given technology or any given skill. We think it's less of an issue for what we're doing, which is we're focused on research jobs that use machine learning. So an overrepresentation of computer and mathematical, like those are the things we want to pay attention to. We don't anticipate there's going to be a lot of research jobs in machine learning in food preparation and serving. And now that we might be totally wrong. That's fair. We don't have the data, but that's the hypothesis we're going through is what we care about is research jobs in machine learning or research jobs in these other technology areas. And so we think Burning Glass has the right kind of data for us. Does that answer your question, Dimitris? Oh, sorry.
Let's think it does.
Okay, let's just think it does, because the logistics of the quick answer aren't really working. Okay. So what we have is, so they scrape job postings and they say they have pretty good technology, it seems, on avoiding showing the same job posting multiple times. So they can identify unique job postings. And then each job posting, they identify a set of skills, and they identify 17,000 skills and 644 skill clusters. And so that's how we're going to focus on those skills and skill clusters that Burning Glass defines. And then we're going to try and map them to a particular set of technologies. So how do we identify our technologies? There's lots of ways to think about identifying technologies. Our first pass, the thing we're going to focus on is we looked at all cover stories in Science and Nature for over a 19-year period and identified of those, lots of cover stories. So, 12 times 19 times 2, those that are engineering, and then conditional on them being engineering, those that were listed as a skill in the Burning Glass data. So what makes the Science and Nature sampling frame make sense? It's of general interest to scientists. It's evidence of cutting edge science. And it gives us something like a independent sampling frame. Of course, it's by no means a complete set of all technologies. And the editors of these magazines, these journals, might put things on the cover in response to hype. So we're not saying one's causing the other. And then there's something that we'll start to unpack later, which is this issue of we are observing a snapshot in time. And quantum computing, we're going to say, is not a general purpose technology, but that might very well be a yet. And 10 years from now or 20 years from now, it might very well be. Okay, so, and then as a side note, we're also using the Gartner hype cycle as our alternative list. So how do we think about the Science and Nature? You can see, you cannot see because it's way smaller than I thought it would be. Here are covers of Science and Nature, like that July 17th one, issue 349, is about artificial intelligence. Okay, and that's going to be the May 15th one is about GIS. And so we're going to look at these covers and then say which ones are technologies. And then we tried to map them to the burning glass. So there's going to be some technologies that just didn't exist in the, no one was hiring for that particular skill, and that didn't make sense. The other way to do this is we just looked at the Gartner hype cycle, sort of the, on emerging technologies, looked through those and tried to figure, and then again, mapped it to what was in our data. So Burning Glass identifies skills, and we're going to use these skills to create these categories of job postings: machine learning, GIS, CRISPR, quantum, etc. And fracking is weird. So fracking, like, let me be clear, we don't think fracking is a general purpose technology. Part of the whole idea here is to see if this is, if the methods we have to identify whether machine learning is likely to be a general purpose technology should also show that some technologies are clearly not. And you may not be surprised. I imagine you're not surprised, but there's not a lot of different industries that are fracking. It tends to be in one. Okay. So they're research oriented. So we have another data challenge in identifying a research job. So we're going to define a research job if it includes at least one skill labeled as research. Okay. And so research methodology, lab research, and we're working on alternative definitions to make sure, we've already made sure that this is robust and doesn't include things like, marketing research, which isn't really the kind of research we're thinking of, and we're working on others on the robustness there. Okay, so here's what the data look like. So you can see, here's an example: senior technology product manager, MuleSoft for Salesforce, and this is a machine learning job, and it really explicitly says machine learning is one of the skills. Okay, in GIS, oh, here's somebody asking for GIS. It's a forestry job. In CRISPR, well, there it is, CRISPR, explicitly right there. Okay. We also are going to use some data on firm size and location size to assess co-invention costs or get a sense of co-invention costs. Okay. Our core results are going to be presented in Gini coefficients. And Gini coefficients are typically used to measure economic inequality, but we're going to, a value of 0 means the skill is widely dispersed, and a value of 1 means it's highly concentrated. And unlike the HHI, Gini helps us capture whether a large number of observations have very little share, as opposed to whether a small number of observations have most of the share. So it's like HHI is often defined the first 3, 4, 5 companies or groups drive concentration, where Gini tends to be a little bit more dispersed. But we could substitute one versus the other. I don't think it would really matter that much. Okay. So I have 9 minutes left or something. Is that right? Okay. So in my remaining 9 minutes, we're gonna present the data. As I said, it's descriptive stats, so I don't think there's going to be. You can argue with the conclusions, but the data is the data. So first point is when we look at total jobs. So this is total jobs over 2015 to 2018 inclusive. That out of these 9 categories, we see lots in cloud computing, and then machine learning is second, robotics is third, GIS and the other Internet of Things, and the others are quite a bit lower. Like there are not a lot of fracking jobs on in Burning Glass, and that might be because they're mostly not research jobs and mathematical jobs, but that's there's not a lot of fracking research jobs going on. Okay, when we look at a wider set of technologies, I'm going to show these. I know that the labels are very small at the bottom. Just know that the first one here is machine learning. Okay, and in AI is basically Watson. So AI, it's weird. AI is not really the way we think about AI. So in the sense that AI is, do you know how to use Watson? And a couple other off-the-shelf text. So it's machine learning, this machine learning column that we're focused on. And you'll notice already machine learning and data science trends look very similar. Okay, let's look at the Gini coefficients. So if we look here, what you can see is machine learning, robotics, and cloud computing are relatively dispersed. They have more jobs and they're relatively dispersed. That, they might be more mature, they're more widespread. We're already seeing that. The big thing we want to focus on though, okay, and then, if we can do it at the firm level, we get roughly the same results, except GIS also looks relatively dispersed. And if we look at the Gini by, for all of our machine learning is somewhere in the middle. So it's somewhat dispersed, and you can, but not, for the overall number of adopters, machine learning looks like it's in the top half, but not really at the cut. There's no clear sense that this is distinct from the other technologies. What makes a GPT distinctive from other technologies, is this potential for research. And so we're going to focus on these research jobs. And I want to just be clear, research jobs are a necessary condition for further innovation. They are not sufficient. So again, this is a suggestive of what's going on. And what we're going to find is there's a lot of research jobs in machine learning. Okay. So cloud computing, even though it had several times as many total jobs as machine learning, it has fewer research jobs. As a percentage of total research jobs, it's 15, machine learning is 15%, cloud is only 2%. Now, notice CRISPR is 78% because who's asking for CRISPR and it's not a research job? That's going to be pretty unusual. It's going to be some kind of management job of people who are doing research. So machine learning has lots of research jobs. And we can see that in the data here, where we look at the count of research job postings, the count is all in machine learning, and this is data science, this other one, which, as he said, looks a lot like machine learning. But as a percentage of jobs, machine learning is in this 15% range, and the other ones like CRISPR and nanotech and quantum that are relatively high in terms of the fraction of all jobs that are research jobs are also very, very small sectors. So we think about, it's not just that there should be lots of research jobs, but they should be across many using industries. And so the next set of results, the next set of descriptive stats, I should call them, highlight that research jobs are relatively dispersed in machine learning, also in robotics and cloud computing. But there's a wide range of research jobs across lots of different industries, and you can see that whether it's defined at the firm level or the industry level. There's lots of different research jobs, and that result is driven, once we compare lots of technologies, lower is more dispersed. It's driven by the most recent years. Okay. And so to summarize all of that dispersion in the newer data, it's hard to, I understand you can't really eyeball it. As I said, this is hot off the press. This is literally hot off the press yesterday. But what's interesting here is that the change from 2010 to 2019 is very large in machine learning. It's large in some other areas, but particularly in machine learning for research, for the dispersion of research jobs. Last set of results I'm thinking about, what does it mean for something to be a general purpose technology is, so this is a heat map where the rows are fraction of jobs on the y-axis that contain the skill on the x-axis, okay? So if you look here in 2010, machine learning jobs, so the fraction of machine learning jobs, a lot of them, you'll see it's pretty white, but okay, so I'm just trying to, okay, so here we can see a lot of machine learning jobs also require the data mining skill. That's what the darker, the the darker thing there means. By 2019, this first column gets much darker, even relative to pretty much everything else there. And what that's saying is the fraction of other types of jobs that require machine learning skills has gone up sharply, even relative to the fraction of machine learning jobs that require other skills. So it's just this first column has gotten darker. Now that's true. This is of all jobs, but if you look at research jobs in particular, that change is even more stark. And we can see that this first column has gotten much darker. We also see the fourth column has gotten much darker, and so that fourth column is data science. And so what we can do is take this, where are we? This table, along with some of the other data we've presented, and just do a cluster analysis of saying, hey, does machine learning pop out as different in terms of these features than the other technologies? We know it's sort of in the top half all across the board and nothing else is, but does it really pop out as distinct? And if we do a cluster analysis, we can see that machine learning and data science pop out together. So their descriptive stats look very similar. Then the other technologies, group together in various ways based on, I think in some sense how mature they are and whether they're research or not research focused. Okay. Last set of results I want to go through very quickly because given the 45-minute presentation, I have to assume that some of you remember this old paper of ours, and if you don't, then you'll have to take the interpretation on faith. And actually, I should say differently. And if you don't, you should go out and read it because it's a fantastic paper. No, just kidding. But so the idea here is the IIS literature has emphasized organizational innovation as key to generating productivity benefits, whether co-invention or organizational complementarities. Now, it's too early to see any change in practice, but what we did in our old paper on the context of the internet is said, look, co-invention we know is cheaper in large cities, and we know it's cheaper in large firms. And so let's just look to see if this technology is disproportionately adopted in large cities and large firms. And the main results, actually most technologies are disproportionately adopted in large cities and large firms, except for the only exception here, well, fracking is not really a surprise, but is the robotics side, where a lot of the leading adopters of robotics are not in, there's no difference between cities and rural areas. And so, and we can do that across all technologies. So the core takeaway there is, if we're going to think about using industry innovation, we can think about using industry innovation as in terms of R&D, which is going to be research jobs. And we can think about using industry innovation as organizational complementarities, as they change the way the organization operates. We have a better measure of R&D, and this is suggestive on the organizational complementarities. If you take the results of our previous paper as, okay, that's a definitive way to do it, which I accept is a big if. Okay, we accept it. Maybe, yeah, let's say we accept it's a big if. Okay. So in the end of the day, you can think about this as a scorecard where machine learning out of these technologies is disproportionate, is relatively consistent with it being a general purpose technology. This is not comparing machine learning to internet or machine learning to, plant agriculture, to agriculture, or machine learning to the steam engine. So we don't have a way to have a comparable data set of the steam engine or even electrification or the first wave of computing. We actually played around with that, but the old style classified ads don't have long lists of skills. So you can't even really do that kind of comparison. But at least relative to these other technologies, Bresnahan and Trachtenberg highlight things that are consistent with GPTs, and machine learning is consistent with it, and cloud computing in many ways is as well. Just to anticipate questions, there's lots of limitations. It's job postings, it's not tech usage, it's not actual hires, it's not all job postings. we can't compare to the internet in 1995 or Steam in 1800. And even the internet, like no one bothers to list in a job posting today that you need to know how to use email. And so we can't even think about in our data whether internet is a GPT or not. And then we capture a particular moment in time. We're working on thinking about it as a 10-year period, but it's not. That's not to say that something might be, some of these other technologies might become a GPT later. So our core contribution, as we see it, is to think about identifying a GPT today and not in the future, and then to identify that relative to other emerging technologies, machine learning seems to be likely to be a GPT. Thank you. I think we have time for a few more questions.
Yeah, all right. Thank you so much, Avi. Actually, yes, this has been very interesting. So you've also gotten a couple of questions here. Let's see how many we can go through. So I'll start with Aninja, who's unmuted now. Yep.
Hey, Avi, how are you?
Good. How you doing?
Good, good. Yeah, so very interesting. So I was trying to, understand, I guess, one high-level question, which is, when you talk about job postings for certain skill sets, there's obviously a lot of overlap between, let's say, data science and business intelligence and big data. So I can see that, if your goal is to essentially isolate within the posting, whether 2 or 3 or more skill sets are mentioned or not, then it's a relatively easy goal. But I also think that it's probably, given where you're going, it's also important to identify how much of an overlap there is, in which case you have to figure out a way to assign weights, right? And so I guess I was curious how did you guys do some text mining of the posting description to figure out the weights of overlap? Or?
We did. So this is, in some sense, the way we're thinking about that problem. Which is that there's 2 conditions. So we're doing pairwise, so pairwise by technology, and we're looking at if the job posting mentions machine learning, how likely is it to also mention all these other technologies? So conditional on the row is conditional on this being a machine learning job. How likely is it to also mention data mining? Okay. And then the column is conditional on being something else. How likely is it to be machine learning? So we're thinking about the way we interpret that is over time, machine learning is becoming more and more central to all sorts of other skills and not really vice versa.
Right. So I guess that means that when you say how likely, you're looking at the presence or the absence of the mention of the other skills.
Yeah.
Right. Okay.
Yeah.
So I guess that's fine. And I was thinking maybe if you could also quantify the extent of the overlap, not just whether it's mentioned or not, but some jobs like blockchain and AI, there's a lot more overlap versus, let's say, AI and, let's say, cloud computing, right? So how much of an overlap there is?
Oh, do you mean within a particular job?
Yeah.
Like,
yeah.
Oh.
Yeah.
That's a good idea. We got to think about within the constraints of our data, whether we can get a meaningful, whether at the end of the day, any data mining we're doing would really, or natural language processing we're doing would just be capturing this figure in a different format, or whether we could do more. Because you can think about maybe it's, job titles, we can see that they're associated with these different skills and then sort of back out. But it's an interesting idea. I just got to think through whether, and huddle with Florenta and think through whether in the data we have more variation than what we have on here in terms of skills.
Sure.
That's a good idea. Thank you.
All right, thank you. Next up, we got Unadi Narang. So, yeah, sorry if I mispronounced names, by the way.
Hey, Unadi, how you doing?
Okay.
Hi, Avi. Good to see you. Thanks for the interesting talk. I was thinking more about the framing, I was curious how you decided to frame this within the general purpose technology framework. One of the things you argue in your book is machine learning brings more scalability, or reduces prediction cost, unit cost per prediction. So I was wondering, when you come to the conclusion of ML is becoming more critical to other jobs, does it have something to do with the scalability aspect, which I don't really see fully covered in the general purpose technology framework? And what is that speed at which the ongoing technology improvements are happening? And does that really matter for the research that you're doing in this paper?
Okay, that's a great question. So in the sense that I haven't thought about it before, and I should have. So we think about whether something's a general purpose technology. It could be scalable. It could be like steam engines aren't really scalable in the same way. So it could be or couldn't be. What's distinctive about this general purpose technology is it's a software, to the extent that it is one. As software, it's scalable. And why, our framework, both in, in the prediction machines book and in the academic work we've done, has emphasized that prediction matters because it helps us make better decisions. And it helps us make decisions at scale. Mm-hmm. And so underlying the only reason why this might be a general purpose technology, why machine learning might matter, is really this, the decision theoretic framework that we emphasize in prediction machines and the other work. So it underlies machine learning as being a general purpose technology, but it doesn't underlie general purpose technologies. And lots of general purpose technologies, like they're, it's knowledge, and knowledge is scalable, but actually sort of implementation isn't scalable in building a steam engine or agriculture or something like that. Yeah, okay. I realize I should probably go to a later slide. Okay, I think we have time for one or two more.
Yeah, we should, exactly. Neil Thompson also has a question, so I'll unmute him.
Hey, Neil.
Hey, Avi.
Yeah.
So I wanted to pick up on something you mentioned earlier about this question of sort of that it's a little hard to have like defined boundaries for these different technologies. And I guess in my mind, I'm sort of thinking of this alternate situation where we think about sort of the rise of quantitative analysis and statistics, right? So if we think about the history of economics, we've really seen in our journals, there's been a huge influx of this, right? You can see that in political science all over the place. And it's because we think that quantitative analysis and statistics that go with it is really important. And I guess I'm wondering about that because I see all over the place when I talk with people sort of a rebranding of what we used to call quantitative analysis and statistics into machine learning, right? So people who do regression now call themselves machine learning experts. And so like some of the growth that you see could just be sort of people rebranding themselves. And I was wondering sort of, what your thoughts are on that. And secondly, whether you've tried to replicate this looking at just deep learning, which as you point out is really the sort of the branch of machine learning that has had the discontinuous change, right? Everything else has been sort of a smooth change, but that one really changes notably in 2012.
Okay, so on the first question, it's hard to identify a rebranding, but the general point that in some sense that rebranding is likely to be slow, in that a job posting that used to say regression is now likely to, in 2010 it might have said regression, in 2015 it might have said regression and machine learning, and today it might just say machine learning. So we should be able to capture that over time through that the cross postings on, and I just showed you the 2010 and the 2019, but we've done it year by year. And so what we have found so far, as I said, is just to emphasize that machine learning and data science are the same thing in many ways. They're this part of the same cluster. The other technologies in some sense are a little bit different. And so it's, we haven't really thought of regression as a skill. I guess we could try that, or statistics, but a lot of the other technologies because we sort of need a sampling frame for it, but your broad point that there is a suite of technologies that have to do with analyzing data, data-driven quantitative analysis that we now call machine learning, and that seems to be a general purpose technology. I think that's 100% consistent with our results, with the caveat that in 2010 it didn't really look like that was a general purpose technology. So that wasn't as widely spread. It's only in the last few years that we've seen it across a wide range of industries as a large, as a large number of jobs. In some sense, you can think about if the way you describe the journals, okay, that trend maybe happened in economics in the 90s, maybe the 2000s. And so industry would be lagging by 10 years. That makes sense. To the okay, what was the second question? Oh, have we done this for deep learning?
Yeah.
There is not a lot of jobs that explicitly say deep learning.
Mm-hmm.
So we can try, we can unpack that at a very high level, and it isn't focused in one particular industry, but the raw numbers are low. And so that might be deep learning is not yet a general purpose technology, or it might be that the HR manager doesn't know to write deep learning and just writes machine learning.
Okay, thanks.
All right. Since we're also close to out of time, I definitely want to give one of our organizers a chance to ask a question as well. So Christian Peukert. Yeah.
So thanks, Avi, for this interesting talk. So I was thinking about the idea that a lot of the follow-on innovation would perhaps happen in downstream firms. And it looks like you're mostly able to identify upstream firms. Have you thought about that? And would there be some way of identifying the more downstream firms in your data?
What do you mean by downstream and upstream?
So downstream meaning firms that use basically the outputs of ML models, and upstream firms would be the ones that you seem to have more in your data, the ones that do actual research in ML and are at the frontier of developing these technologies.
I think our data is the opposite. I think our data is overwhelmingly using industries. So, this is retail. This is across lots and lots of NAICS. The information NAICS is only a small percentage of our data. So I think these is mostly using IT in a machine learning using industries, not producing. They're hiring and research. So these are jobs that have researchers. Walmart has a huge research department. But I think of Walmart as a using, not a producing firm.
All right.
All right. So I think maybe, in order for us not to go over time too much, maybe this is a nice stopping point. We have a couple more questions that I can definitely send to you, Avi.
Right.
So some good suggestions here as well. So sorry if we didn't get to your questions, but yeah, who wants to maybe, again, thank you just for this very interesting talk. Who wants to announce next week's speaker? Or is that? Okay.
I guess I'll do that. So thanks, everyone. Thanks, Avi, again for presenting. Next week's speaker will be Catherine Tucker from MIT. She'll present some new work on digital divide and the coronavirus. So definitely something very relevant these days. We hope to see you next week. Same time, same place, like probably for most of us. And thanks everyone for attending. Bye-bye.
Yeah, thank you all.
Thank you. Bye, everyone.